Okay, so today, we're going to start talking about it, rational expressions here. That's basically, this is basically the last topic on the, for the course. So, the word rational here refers to, if you look just like, first five letters, the ratio, so it is about ratios, so this has to do, is related to ratios, so. So when you have like, when it's like when you refer to it, so if you say rational expressions, like it is something that involves a ratio, so. Um, Written as a ratio. So for example, let's better do or like some examples. Like basically anything that you could write like as a ratio, so you could like, um, 3/5 is like a very simple rational expression that's not as interesting for us. But what's a little bit more interesting is when it starts depending on x. So you could write something like 3 plus x over 5. That is a rational expression. Then both the numerator and the denominator can depend on x. So you could have x over 1 minus x. That's also a rational expression. It can even depend on x and y or more variables, although like usually like the only examples I'll be doing for the course like only depends on x, but you know, something like x plus y squared plus xy over 3 plus x minus y. That would also be a rational expression. So basically anything that you can write as a ratio would count as a rational expression. It can even like involve square roots, that's fine. So you could have something like this. That also would count. So basically for us, the expressions that we'll work with, for us, a rational expression would just be like a numerator that depends on x and a denominator that can possibly depend on x. So, for us, so this is going to be any formula that you can write as. Okay, so here f of x and g of x, you think of them as functions of x. So here, okay. So the basic goal with these will be to solve equations. That's kind of where we're headed at. That's what we'll do tomorrow. How to solve for equations that depend on x, but are also like fractional. Today, what we're just kind of going to go over is like the basics of how do you simplify fractions. Uh, which is like useful to get, you know, refresh your memory on that because that's important for tomorrow's class on how to actually solve equations. So, let me give you like the rules for simplifying fractions. Or not just simplifying, but just like what are the rules involving fractions? Okay. Um, so the first one, I'll put, I will kind of start with the most basic ones. So the first one is that, you know, which we have discussed, like, I did almost even on the first day of class, right? Like having denominator one is, you might as well not have anything. So like if you're dividing by one, that is just like the numerator, right? So like, here's some examples, like, x plus two over one is just x plus two. Like, it doesn't matter how complicated the expression is. That is a problem. X squared minus x plus one, that, that just gives you whatever the numerator is. So this is like the first property that is important to remember. Okay. The second property is kind of like a rescaling. If you want to call it like that. Which is kind of like a more interesting property, to be fair. So which, like, so what this one it says is like, imagine that you have like a fraction. Oops, like I actually take it back. So I was thinking it should have been A and C. Okay, imagine you have a fraction. Okay, but like the numerator, like there's like this quantity A that appears both in the numerator and the denominator. Okay, under multiplication. So it has to be appearing as a product. So one way to think about it is that you're you're making B 8 times bigger and you're making C 8 times bigger. So like you're making both the numerator and the denominator bigger by that same amount. So it's kind of like a stretching factor. So like imagine, like, just to make it like more concrete, but it's kind of useful to put numbers into this. Just gonna make, like, write it with some specific numbers. Like if you have B and C and you multiply each by 2, so that you are doubling B and you're doubling C, right? So because the stretching, like, or the rescaling, that's another way to refer to when you stretch something. The rescaling is by exactly the same amount, the ratio remains the same. So the formula, what the rescaling formula says is that whenever you have a fraction and the same quantity appears at the top and the bottom, it kind of disappears, basically. So this is B over C. Okay. But it is like crucial that like to have the same amount in the numerator and the denominator. So just to give you some examples, here are some examples of, so like, well, for like the first example would be like what I just said, like that 2B over 2C over C. But like, more concretely, the way we'll think about it is, say, for example, you have 3x over 3x plus 3. Okay, so this is actually like the type of thing that we'll try to do today, like simplifications. Like, so how can you think about something like this? So like the numerator is 3x, the denominator is 3x plus 3, but it is convenient to, in this case, kind of factor out at the bottom a 3. Okay. So far, so good. Everyone with me. And then the reason for doing that is that now you have a 3 kind of more explicitly both at the top and the bottom, right? So since it's 3 here and 3 here, like that goes away because it is like the same amount both in the numerator and the denominator. So you end up with x over x plus 1. Okay, so that is kind of how, like, so let me just erase this a little bit. That is more or less how you would want to start using like this, like rescaling property, for example, that when like you find something that appears in the same amount in both the numerator and the denominator, and you kind of like get rid of it. Here's another one. If I had x squared plus x, and let's say, just to make it easy, because like later we'll do more interesting examples, like after I kind of run through all the formulas. So if I have x squared plus x and x squared minus x, what can you do here? So the numerator, there's like an x that you can factor out. And so you get, when you factor out an x, you get 1 plus sorry, x plus one. Okay, and the denominator, there's also like an x that you can factor out. Here you get x minus one. Okay, so now it's gonna look weird, but like both x, like now the numerator is kind of being stretched by x, and the denominator is being stretched by x as well. So it's the same amount of stretching, and so that is why you get x plus one over x minus one. Well, maybe I should put in color like the thing that is the same in both cases. So 3 and 3 is what it appears here, repeated, and x and x is what appears repeated in this case. Let me just. But it is important that it is under multiplication. So like you can only do the cancellations when you're doing like multiplication. Otherwise, like that doesn't work whatsoever. So whenever kind of what we will do today is kind of a clever combination of factorization with these rules to start simplifying how the expression looks like, because the idea is that it is easier to work with something like this as opposed to working with something like this, which has like extra stuff that is not really required. Okay. Here's another one. Yeah, that can be confusing, which is like involving the negative sign. So I'll write them all like later, like on the board, like on a side of. Oh, actually, I'll put them there. Let me like put them here so that I can refer to them later. So A over one equals A. The other one is like A, which is A over C over A. Okay, so what is the formula for like the property of the negative signs, which is, which probably you have seen it before, that when you have a negative sign, like, or this refers to the opposite of the number or like the expression A over B. That minus sign, like, can be put like either in the numerator or the denominator. So one way to think about it is like, this is like negative A over B, if you like, but you can also think about it as A over negative B. The important thing is like, if there's like a minus sign, it has to appear this once somewhere. So it is up to you whether it appears in the numerator or the denominator. Typically, it kind of looks odd to have like a minus sign in the denominator. So like the way this is usually used is to kind of like not put like the minus sign on the numerator. So for example, what I'm trying to say is that if you have something like as 2 over negative 3, it is kind of like ugly to have like the negative 3 at the bottom. So like it can be moved up without any like any worries. So you can put it like. So this is the same as like negative 2 over 3. And like this minus sign, like it can be thought about like kind of like as affecting the entire fraction. But then this minus 2/3. Like, so it doesn't matter, like the important thing is like it appears like it doesn't matter where you place it, it just has to appear once if there was a minus sign on the expression. That can be useful sometimes if again, like to kind of for like aesthetic purposes, but also for simplification purposes. So for example, let's see if I can. Here's like a more interesting one, which again, like we're kind of like trying to get used to like simplifications. So let's say I had. This is like actually a bit more interesting. So what's going to happen here? Okay, so I'll leave the numerator as x minus 1. And then what I can do is factor out an x at the bottom, right? So I'll factor this out here. 1 minus x. Right, so far so good. But now, what's kind of like interesting is like you see like you could say, well, the numerator like x minus 1 and 1 minus x are almost the same. They just kind of like have like the opposite, like the incorrect signs. So if you want to simplify this can be simplified, but you kind of have to do a little bit extra work. So one way to do this, like to simplify this further, which is what I'm trying to get at with the properties of simplification, is that, for example, you could have something like this. I'll put like the numerator x minus 1, and kind of like I want x to start with a positive value. So, one way to do that is like to kind of like factor out a -1 at that, like for x minus 1. And the effect of doing that is that it flips the sign. So like you get x minus 1 here. Okay. So like just to actually let me put it like in the colors to like kind of clarify what I'm trying to do. So I had 1 and I'll write it as -1 times x minus 1. That's clear, like, because what's going on here? If you do like the product, you get -1 times x. The -1 times x gives you this minus x that you see here, and then -1 times -1 gives you the +1 that you see here. So these multiplies to 1 minus x again. But what is the advantage of doing that? That then, like the numerator is x minus 1 times 1, if you like, just to make this more clear. And then I'll kind of just like rearrange the factors here. Like, so I'll put this as the first one, but you put x minus 1 times x times -1. Okay, and so what can I do here to simplify any further? Like, you have x minus 1 at the top and bottom, so you can get rid of it. So you end up with 1 over x times -1. But as I said, it kind of looks weird to have like the -1, the -1 at the bottom, so you can move it up. So like, it is 1 over minus x, which is -1 over x, for example. That is one way to do that. Maybe this is so this is like kind of like a topic where like a lot of like the things we have been using kind of like all come together. Like, at first it can gonna take some time to just like, you know, become comfortable like using different properties at once. Because like if you see like there are a couple of like there are a lot of things happening just here to simplify this. So it's like a good topic, like that's kind of why it's a good ending to like in terms of topics to the course, because really like a lot of the stuff we have been doing like comes together here because like there's a lot of properties involved in general. But let me put this other extra property here. Again, today we're mostly just going to do this simplification of fractions or fractional rational expressions. And then the last one that is important to have is like a formula for how adding fractions behave. Okay, so here's the last property that you need to know. And everything else kind of like require, like we'll use those properties in some way or another. So the last one is like the property for adding fractions. So to add fractions, Let me just check it. Which one I call the numerator here? Okay. So the property for adding fractions is that as long as the denominator is the same, you can just add fractions by adding the numerators. Okay, so like you can, like when adding fractions, you can add the numerators provided the denominators are exactly the same. Yes.
I was trying to look at that bottom example, where did you get the extra -1 from, what after the factor? How did you pick on that?
Like here?
Yeah,
The thing is like, if you compare the numerator and the denominator, right? These two things are almost the same, but they have opposite sides. So kind of like I'm forcing it to look exactly the same.
that property, okay.
Yeah, by like kind of, but you can always double check just by doing the product. So if you do this product, you get like -1 times x, which gives you the negative x, and -1 times -1 gives you this +1. But I kind of like artificially pull it out so that like it looks like identical to the stuff on the numerator, so that I can cancel it out if that makes sense.
That makes sense, thank you.
It sure makes. But yeah, it's like, you know, it is a clever, like, you know, the thing with like this, like, so I'm kind of like factoring a minus a -1, but it's not super obvious, right? Like as other factorizations. But so that is like a convenient trick because like, yeah, there are many times like the two things are exactly the same except for like an overall sign, and then in that case you can do that to get like to take care of it. So it's kind of like useful to write this in words. So what I'm saying here is like you can add the numerators provided both fractions have the same denominator. So you can add the numerator as long as the denominators are the same, and that's like actually pretty important. So one, like, you know, let me write some examples that like, and then do like some more complicated ones. And you know, like, one way to convince yourself of like a formula of that sort is like just like thinking about it like in a couple of small cases. So like imagine like, you know, if I get giving you something like 2/5 plus 1/5. So what's happening here, like, you know, one way to think about the fractions is like, you know, you have like a spender ruler or like something like of unit length, right? So 2/5, what does that mean? That means that you break it into 5 pieces. So let me see if I, you know, you break it into 5 pieces, each piece of like the exact same size, and 2/5 represents two of like these blocks, okay? And then the other one, like you're doing the same. You know, you're breaking it into 5 pieces. Well, like should have like the same height because like they're exactly like 2 copies of the same ruler. So you're breaking it into 5 pieces. You know, and then you know, you're just adding blocks, stacking blocks together, and then that's why how you end up with 3/5. Or like actually like 2 plus 1/5, which is 3/5. So it's kind of like I mean, like, you know, kind of like doing it with like positive numbers, to just like show you how it goes. But it's like that's why like the property is kind of like intuitive. as long as the denominator, happens to be the same, because like, for example, if you did something like, um. Let's say, what happens if you do 2/3 plus 1/3, you know, here you have like, the same ruler, which you broke into 5 pieces, right? And then the other ruler, but now this one you're breaking into 3 pieces, right? So it's kind of a bit of like an apples to our oranges comparison now, because it is not like this, like you're kind of like breaking the ruler, but like in different amounts. So like you can like, of course, like you can, like the addition literally corresponds to just putting like this one next to this and seeing what like that corresponds to. But it's not super like obvious like, from the picture how to do it just like that. So that is where like you kind of rely on the other properties of the fractions to kind of like set them up so that they have the same denominator. That's like the trick, which is what as like find the common denominator or whatever, like for the fractions, right? So, one way to do it is like, well, like you kind of just think, what is this fraction lacking? Like we don't have the 3 that appears in this denominator, right? Or like the 3 that appears in the denominator of the second fraction. So you kind of put it by brute force. So how can you prove something by brute force? Well, using the rescaling property, because you're allowed to stretch things by the same amount. So essentially what I do here is to multiply the top and the bottom by 3 because there's a 3 missing in the first fraction. Okay. So that will guarantee that like the first fraction has like a 3 in the denominator. But then like what is happening with the second fraction? Now the second fraction is lacking a 5, right? So like I just force it to become I just force like the 5 to show up by multiplying and dividing by 5. Which you can always do because like that's why this rescaling property is useful, because it says you can multiply like a fraction by a number as long as the number is the same in the top and the bottom. So that is like the cool thing about that property. So if you think about it, what ends up happening here? Like the numerator 2 times 3 is just 6, and 5 times 3 is 15, and the numerator here is 5 and the denominator is 3 times 5 is 15. Okay, so essentially it's kind of like a conversion, like where since this ruler has been broken into 5 pieces and this one into 3, you kind of like chop each of these into 3 mini blocks and these blocks into 5 mini blocks, so that there's like a kind of like common cut to both of them. And once you have it in this format, then yeah, you can just add them like numerically by adding the numerators, like 6 plus 5 is 11. So that would give you 11/15. Is that making sense? So it is kind of like a cute trick of rescaling, so that it does look like you're kind of like like again, like the denominator kind of tells you into how many pieces you're cutting like the numerator. So like you have to make the cuts like of the same amount so that you can actually compare it. Otherwise, it's kind of like adding euros with dollars. You cannot really add those together because they have like different units. Like if there's like a kind of like a gold reference, like a gold bar, like the dollars would correspond to certain pieces of the gold bar, the euros to a certain pieces of the gold bar. And then you cannot really add them unless you kind of like cut the gold bar by the same thinner amount. Equal. Is that making sense? But the cool thing is like you can like kind of the point of doing it is that it is like the nice thing is that you can add these 4 things that are not just like with numbers in the numerator and the denominator. Like you can have expressions that depend on x and do the same trick. So let me see if I can give you some good examples here. Oh yeah, let's do this one actually. I'll just erase like the top one. Here's like a more interesting example, and this is again like the type of thing that we're going to be practicing today. So So the nice thing about this is it's kind of like there are two ways to do the addition. And one is kind of more clever than the other because in one option you factorize first and make your life a bit easier. Okay. So I'll kind of do it both ways to show you like the advantages of factorizing as much as possible before like adding. But I'll kind of do it like first a longer way to kind of like show you what's going to happen. Okay. So So option one will be kind of like without factorizing. Again, option two will be factorizing before adding. Okay. So like I'll call it like adding before without factorizing first. So what's going to happen here? So again, like you cannot add them as they are, as they appear because their denominators are not the same. So if you're not factoring anything out first, what you can see is like, okay, I have to force these denominators to be the same, right? And then you can say, okay, for the first fraction, right? What is missing here? Like, well, like the first fraction doesn't seem to have like an x squared minus 4, so like you just put it by brute force, like literally that's just what you're doing. So you just rescale the numerator, denominator here by x squared minus 4. X squared minus 4. Okay. And then the second fraction, right? Well, it looks as if it's missing an x plus 2, so you kind of like just put it by brute force, like top and bottom. Okay, so I'll put this like x plus 2 at and I'll put this, I'll kind of put this in parentheses too. So far, so good, it's making sense. So put this up to this point. Okay, so let's see. So now just kind of like do this extra step. So yeah, you multiply the numerators, multiply the denominators. And then multiply the numerators, multiply the denominators. Okay. Now the denominators are all the same. So you can just add the numerators as they are. So like you can just do, well, what's the first numerator is 3x squared minus 12 if you like. And the second one is like 5x plus 10, right? So you can do that. And then you have x plus 2 times x squared minus 4 in the denominator, which is the same. And that gives you what? It gives you 3x squared plus 5x minus 2 over x plus 2.
Take the floor out.
Uh,
The -12 plus 10.
yes, that's it becomes right, -2 because of that. And then okay, let's see what. Then you can factor this numerator out because like what It is. Let me check if this is the one that works. 6x. This is correct. Okay, what gives you 3x squared plus 6x minus 2. Okay, so this is like a factorization that's possible. Okay. Actually, like this will be longer, so that's why I will show you why you just made your life harder, more complicated. So like, don't pay too much attention to this. Like, I'm just like trying to show you why this is longer. Like, is it longer in particular because you have to think about how to factor out the numerator, which is a mess. So, but then if you factor it out, like you see, x plus 2 is the same at the top and the bottom, right? Like, it's like x plus, like, let me call it. This let me call it. There's an x plus 2 here, an x plus 3 here. Well, it gives you 3x minus 1 over x squared minus 1. Is that right?
So that's the reason why I cancel out on the top, because, like, whereas, 3x² minus 4 over x plus 2. Right there, yeah,
Oh, right,
these
right,
two
right.
Canceled out because they're on the top of the bottom.
Correct. The thing is like, so if you do it this way, I kind of, I did all the cancellations onto the very end. But yeah, like basically the cancellation comes from there being like an x plus 2 keyed in the numerator. It's not super clear unless you factor it out, right? But yeah, like that's actually why this is longer, because you haven't taken advantage of the fact that you could have like kind of simplified a bit earlier. Right, and so that's kind of what I'm going to kind of go through right now. But yeah, like the point is that if you don't notice it, because it's possible not to notice it, like you can still like take care of it at the very end. Okay, but it's kind of like hard, like it's kind of like trickier, like or easier to run into issues when you factor this one out at this step. So that's why it's kind of like better to avoid that as much as possible. But yeah, like what I'm going to do now is kind of like do it in the more like efficient way, which is to factor as much as you can before adding, and that actually helps you a lot to simplify things. Is that making sense? So option 2 is to factor as much as possible before adding. So like, let me put it here. I'll erase a little bit in a second, but if you give me a chance to copy this. So option 2 is to factor as much as you can before adding. Okay. So what happens here if you do that? So there's nothing that you can factor in the numerator in this first fraction, that it is as it is, like that's what it is. But like for the second fraction, 4 is 2 squared, so this is x squared minus 2 squared. So like you can use like the difference of square formulas. Like let me put it here. I'll use like this formula that a squared minus b squared is a minus b times a plus b. Okay, so if you do that, then these can be rewritten as x minus 2 times x plus 2. That's something we have done before, but that is like the advantage of factoring out at that stage. Okay. Let me put it in orange because I'm using the formula there. So I'm just using the difference of square formula here, which is actually one of the most important formulas on the entire course. Like that really does appear like very often in future courses, and we have to take like more more math classes, this is kind of one of the more useful formulas, identities that we see. Okay, so what's the advantage of having factorized first? Then you see like that you kind of did a bit of an overkill when you were rescaling, because here you just what you notice if you factor is that x plus 2 is already present in the second fraction, which was not super obvious before. So like actually this was a little bit unnecessary, and in fact it's a little bit unnecessary. Like when I multiplied by, everything's a bit unnecessary here. Like you could have done that a bit more efficiently. So if you factor out, then you say, okay, why is the first fraction missing? So the first fraction is now missing. X plus 2 is here and it's already here. So like the only thing that the first fraction is missing is x minus 2. So you multiply and divide by x minus 2. I'll use the same color so that you can see the difference here. So the only thing that's missing now is x minus 2. Okay. And in the second one, right? What's happening with the second one? Like it has everything, it already has x plus 2, and you're going to force like the first fraction to have like an x minus 2. So like actually there's the advantage of doing this is that there's nothing that the second fraction needs. Like it will have the correct denominator after we're done with the first one. So like the nice thing about this like doing it this way is that you see like the denominator is already good here. Like it has x minus 2, which is already in this one as well, and it has like x plus 2, which is here. Okay, so like the advantage of having factor out first is that you have to multiply or rescale by way less complicated expressions, like in the next step. Does that make sense? I'll do another example, which is just like this, like in a second, like just with this method, so that like kind of sticks better. But so what is like so the first like fraction becomes like just multiply numerators, multiply denominators, and you have like the second one, which is just this. Okay, and then you get, what do you get? You get 3x minus 6 plus 5. That's what you get when you add the numerators. And that's just 3x minus 1 over x plus 2 times x minus 3. I mean, just separate this with colors. Which is exactly what we had here, but it's a lot less painful to get here than as with the other approach. So any approach like that's kind of like the thing. There are many roads that lead to lead to the same place, but there's some that take you longer, So there's nothing wrong doing it this way. It's just like risk, you increase your chances of making mistakes along the road because like you're working with more like longer expressions and you have to do more complicated simplifications, etc. Okay, so that's kind of like where like what you try to avoid as much as possible to these type of problems, because you want to simplify the smallest things like that available to you. Does that make sense? Okay, so let's do another one like of this sort, and then we can do the quiz. Then I'll give you some other problems for you to work. And this is kind of like the most complicated part involving the fractions, like the rational expressions. Like just to factorize first, you kind of rearrange it so that the denominators are always the same. But that's very important. So like you always need to get to that point where like the denominators are the same. So I'll put so here. So for example, let's say you have. So again, to simplify this, you want to. Because of like what we usually like the optimal method, the best method is to factor out as much as possible. So in the numerator, there's nothing really to factor out, so I'll just leave it as x. But the denominator, this first denominator can be factored out. That's something like this is one of those that you can just eyeball. So like you got like x plus 2 times x plus 3. Okay, so that's the first one. And the second one is kind of like the difference of square actually, because 9 is 3 squared, so it's more or less this same type of problem, so it's like x over x minus 3 times x plus 3. Okay. Does that make sense? What's the advantage of having done that? Because by factoring, you realize that there was an x plus 3 that they both share. So that means that you don't have to worry about that one, it's already there. So like the rescaling only involves like what the other is missing, but x plus 3 is present in both terms, so like you don't have to multiply anything involving x plus 3. So so what is the first fraction missing? Like the first fraction doesn't have like an x minus 3 in in the denominator, so I'll multiply and divide by x minus 3. Okay. And what is the second fraction missing? The second fraction is missing an x plus 2. There's no x plus 2 in the denominator, so I will multiply by x plus 2 in the denominator for the second fraction. Uh, sorry, I should have like copied this one wrong. This one less. Yeah, that was fine. Like, yeah, like I also recommend here like double checking every single step, because when you copy paste, like you're from one line to the other, it's very easy to like, accidentally repeat something. Especially like if the expressions look a bit similar. So. Like from a distance, it's easier to just kind of see that that's fine, but like if you're just like right next to what you're writing, it is easier to get lost and like accidentally make a mistake. So. Then, yeah, like the first, again, like you multiply numerators and denominators, so you get x times x minus 3. And then this one gives you x plus 2 times x plus 3 times x minus 3. And the other one is x times x plus 2. And then this is x minus 3, x plus 3, x plus 2. In fact, let me do the product, like maybe, what is the first numerator? You distribute, right? Like x times x minus 3 gives you x squared minus 3x. There's the first numerator, and what the second numerator is x with x plus 2, which distributes, so it's x squared plus 2x. Just to make it a bit better. And then you just, because now the denominators are the same, you can add them together by adding like the numerator, so you get x squared minus 3x plus x squared plus 2x divided by x plus 2 times x plus 3 times x minus 3. Okay. And that gives you what? Yeah, the first, like the thing with x squared is 2x squared, and then minus x. X times 2x minus 1. Here. Oh, no, that's fine. Fine. But these are like, relatively long problems because like there are a couple, like a lot of like a lot of stuff is going on here, when you're simplifying, the problem. So like, like in a sense, this is like the most convenient way to leave the expression. So there's no, because like, it kind of makes it obvious that there was nothing else we could, easily simplify. So like I would just leave it as it is, like kind of, also like if you had multiplied the numerator and write it as 2x squared minus x, that's fine. But it is better to kind of like leave it as, in a way where the numerator is simplified as much as, it's factor out as much as possible. And the same for the denominator, so that it's very clear that there was nothing else that you could have done. And then again, like that will be useful tomorrow, because tomorrow we'll solve equations involving fractional, expression. So like the type of problem we'll do tomorrow is one where like these would have been equated to one, for example. So you want to solve something like these two fractions add up to one. So what is the value of x that works? And so tomorrow we'll go over that type of thing. So tomorrow we'll do like the version where everything's being set equal to a number. But for that, it's kind of like useful to kind of get used first to the part of like, let's just simplify as much as possible before getting to the type of problem when there's like an equation involved. Okay. Any questions about this? Okay, so let's end here and then I'll do the quiz.